Okay, let's begin. So in the last class, we started to look at the sampling network, and the simplest circuit we came up with was this track and hold. It basically consisted of a simple switch and a capacitor. Then we started to see how to implement the switch, and this was done using a transistor. So the first candidate we had was this MOS transistor. But then we noted that a MOS transistor is far from an ideal switch. So we decided to see the effects of the non-idealities. And the first non-ideality we considered was when the MOS transistor is on, ideally it's supposed to present a short circuit between these 2 points. But in practice it will have some on resistance. So to model this, you can include a series resistance along with the switch. Silent, useful. Yeah. And also to jog your memory, recollect that switches used in our circuits can essentially see 2 kinds of inputs. One is a time varying signal. That will be the signal the front end sampling switch sees. And almost always we typically do some kind of processing on the sample signal before we do quantizing. So the signal seen by the succeeding stages will kind of be held, because if I look at the output of my first track and hold, it's going to be like this. It's going to track, hold, something like this. Now my second stage will be interested in this part of the waveform, which is the sample signal. So the signal the second switches or the switches in the succeeding stages see will be a constant or a held signal. So we decided to see what will happen with on resistance for both cases. So first we looked at a DC case, that is a constant. So let's say this was this. Let me quickly refresh this. Let's say it's some V in 0 and the switch is, let us say, closed at some time instant equal to 0. This is your vanilla first order RC circuit. So the output will exponentially rise and eventually settle to the final value V in 0, right? And remember, the clock is something like this. So if the clock duration is Ts, for how long is the switch on for? Ts by 2. So you're interested in the value at, say, some time instant Ts by 2. Okay, this is Ts by 2. So now you see that if the on resistance is not small enough, you might not be, like reaching the ideal value. It will be slightly off. So to reduce this error, how should you choose my time constant? Less than what? Much less than the time for which the switch is on. This is what you do. Right? So this is what will happen if you have a constant or a held signal. Similarly, we also did for a time varying signal, and for a time varying signal we considered a cos or a sine, because any signal can be decomposed as a bunch of sinusoids. So once again, if I assume that the switch is closed, we know that the output will have some transient, which I didn't explain in detail, that will basically decay with time. Right around C. And what will be the steady state amplitude of the sine wave? You'll have some cos, but what will be the amplitude of the sine wave? Remember, this is a sinusoid going through an LTI system. What is the transfer function h of j omega for this? 1 plus j omega RC. So it's a sinusoid. You guys know, hopefully, sinusoid is an eigenfunction for LTI systems. So it just scales the magnitude and shifts the waveform. So the amplitude will be shifted by or scaled by this factor, omega naught square. Similarly, I'll have the phase will be and as usual, you are interested in the value at Ts by 2 for a duration of Ts by 2. So here, first of all, if you make RC to be much smaller than Ts by 2, this first term nicely goes to 0, no issues. Whereas the second term, as you see, you have some error. So if you want to reduce this error, what do you choose? Basically, what do you want this term to be exactly? You want the amplitude to be 1, phase to be 0. So to guarantee that, what should you do? You need to ensure that this factor is as small as possible compared to 1. That's what you want. Cool. So then we, after recognizing this, we decided to see a MOS transistor. So first we looked at an NMOS. So let's quickly do this. So when it, what do you do for turning this MOSFET off? What do you apply at the gate? So this, you make it 0. And to turn it on, what do you do at the gate? So let's say this is V in. Make some space. So this is the sampling capacitor. I applied VDD. What do you get here at the output? Yeah, last class someone mentioned this is VDD minus VDH. I brushed up quickly. I mean, but why did this came about? Or like, can you have? Do you know? I mean, do you think for some case this can reach only till VDD minus VDH? So why is this happening? Why did you say last class? Yeah, I mean, see, the thing is, let's say input is, let's say, greater than VDD, for example.
We are assuming that the MOSFET is in saturation.
No, MOSFET is never in saturation here. Think about it. If MOSFET is off, which region it is operating? When it is acting like a good switch, V in appears here. What is the drain to source voltage? This is V in, this is also V in. A minus A is 0. So what region it is operating? Linear region. It's never in saturation. Okay. So I mean, let's say V in is greater than VDD, and the voltage is, output is initially 0. This is, let us say, V in. So initially you have a large gate to source voltage. The current, will there be a current? So the current flows through the capacitor. What will happen to the capacitor voltage? It will increase. As the capacitor voltage increases, what can you say about the gate to source voltage? So the current will also reduce. So this will go at a slower rate, and as this increases, current is reducing. What is the minimum current you can have? 0, and that will happen for what value of VGS? VTH. So this will reach what value? So this will happen if the input is really large, but let's say my input here is like really this much. So it will rise here and nicely settle. Right? So once my output reaches my V in, drain to source voltage is 0. If the drain to source voltage is 0, what is the current? 0. It's in linear region, current is proportional to VDS. So once my drain to source voltage drops to 0, no current flows, the capacitor voltage doesn't change. Fine. So these things will happen only if you have voltages greater than VDD. So again, if you remember these results from somewhere you learnt, my suggestion is first unlearn everything and kind of start to learn again, because that is a first thing before learning something new, right? If you have encountered this at some place, but if you just remember the result, not the actual underlying principles, please have a blank mind, unlearn everything and then do this. So hopefully this is clear. So I'll erase this for now. So yeah, my okay, this here, yeah, V out is V in approximately, so VDS is roughly 0, and of course we kind of found the on resistance. I'll just write the expression directly. This is not difficult to prove. This was mu and Cox W by L times the VGS minus VTH. So when the NMOS is on, what is the gate voltage? VDD. So let me actually substitute this fully. Mu and Cox W by L. VDD minus what is the source voltage? When it's acting, my source is also approximately at V in. So now if I try to go and sketch the on resistance as a function of the applied input voltage, this is a simple shifted hyperbola. So it asymptotically goes to infinity at this voltage, right? So that's the same thing as voltage as the input voltage reaches closer and closer to VDD, the on resistance is large, so this is not passing my input as it should be. Cool. So from this, one thing is clear, my NMOS is a good switch for within codes low values of Vin. How low it should be depends on what is the on resistance you can have in your circuit. So secondly, let us say, look at this expression for the on resistance. If you were to control or change the on resistance, what are the parameters that are available to you? Huh? I mean, VDD, let's say it's fixed, we can't keep changing, right? Vin is not under your control. Vin is what someone will feed you, right? Yeah. Only W and L, right? Mu1 is, whatever, COX is constant. Vin is not under your control. Threshold is not under your control. Even supply will be fixed for a particular supply, process. So only W and L. So how would you choose your length so that the on resistance is smaller? Yeah, you try to use the smallest possible length that is available. So with respect to switch, it doesn't make any sense from the point of view of on resistance to use a non-minimum length. Fine? And then you change W to get whatever around you. And also, if you see, even if my input is small, if I restrict my input in the small range, or let us say input is in this small range, if my input changes in this range, even the on resistance changes because my on resistance is a function of the input. So that is not a great news because as we saw here, if I have a time varying signal, the steady state voltage looks like this. So here I find that my on resistance is a function of the input. It's a linear function, non-linear function, doesn't matter. The mere fact that it is dependent on the input makes this entire thing non-linear, right? Because here with respect to the amplitude we have 1 by square root of something, obviously non-linear, tan inverse of something, definitely non-linear. So what this means is if you use an NMOS switch and apply a time varying signal, although the amplitude of the time varying signal is small, right, reasonably small, you take the output samples and plot its spectrum along with the input fundamental tone. What you will observe? Harmonics. Okay, so straight away going to introduce nonlinearity in your circuit. So if you want to reduce this effect of nonlinearity, from this expression, what is the only control you have? Let's say it's fixed by something else, but what is the choice you can make? Yeah, the point is you keep this factor smaller because nonlinearity is arising basically because of these two factors. The smaller you keep omega RC with respect to 1, the smaller will be a nonlinearity. Okay? That's what you are indirectly saying, right? So again, that brings up to second thing. So let me mark it here.
You mentioned Vin is not in a control bias.
Vin is it's a signal that you are sensing from some other circuit, right? So you cannot decide what my input should be. Fine. So let me write it. So if you have time varying signal, you'll have nonlinearity, and the only control knob you have is to keep this guy as small as possible. So which means let us say I do 2 experiments. Let us say in first experiment I apply a sinusoid with a frequency omega 1. Second, I apply a sinusoid at a frequency omega 2. Say omega 1 is much smaller than omega 2. I look at the output samples in both cases and look at the output spectrum. In which case do you think the harmonic strength will be higher? Omega 2 or omega 1? Why? As you see, this has to be smaller. If you have a smaller frequency, this is going to be smaller, so obviously it's more linear. Right? So it works well as long as your input frequency is also smaller. But let us say you want to sample faster and faster, which is what you essentially want in practice. My sampling speed increases, which means the omega naught that also will increase. So in that case, to keep the same level of linearity as, let us say, for a smaller speed, I should, how should I choose the on resistance to be? I should reduce it further. If I increase my sampling speed, I should also reduce my on resistance. So from this expression, what is the thing you can do to reduce on resistance? Yeah, I should decrease the width. So let me write it here. If I increase Fs, my non-linearity increases, which means I should keep, yeah, I will reduce R on, which means I have to go and increase width. Fine. So what do you think might be a downside with increasing the width? Okay. Capacitance increases. So no. What capacitance are you talking about? If I increase the size of the transistor, which capacitance increases? Yeah, where parasitic capacitor I have 1, 2, 3 nodes here. Which node? Mostly at the gate, right? I mean, even if you don't know the MOS device construction, if I increase the area, capacitance is directly proportional to area. Overall capacitance will increase, right? In principle, at all the nodes, it's going to increase, okay? But let us say this is driven by an ideal voltage source. You put an elephant here, nothing changes. So let us say the capacitance here is already large enough that any extra capacitance you add is not an issue. So here is where the other capacitance is. So let's say the gate capacitance increases, what's the issue? Slower? Can you explain?
While applying the signal at the gate, it will take time.
Yeah, so as he's pointing out, remember that I have to feed in a clock signal to the control terminal of the switch. That is a digital signal going from 0 to VDD. So this will be basically driven by a bunch of clock buffers, which is a series of CMOS inverters. I have a larger capacitance now, so which means I should pump in larger charge to the capacitance. If the charge I should push here is higher, the current consumed by the inverters will be more. Okay. So the downside of this is I'll end up burning higher power in the clock drivers. Fine. So that's the issue if you have a larger gate capacitance, right? If capacitance at that node increases, the only person who will worry about it is the guy driving that node. Right? Cool. Yeah. So this is so bottom line. NMOS is a good switch as long as you have constant signals or held signals which are within quotes small enough. But for time varying signals, it introduces non-linearity because my on resistance is a function of the input voltage. And to reduce the non-linearity, you should reduce the on resistance, and that means increase the width. That in turn increases the capacitance and increases the power in the clock driver path. Cool. So now we have NMOS that works well for low inputs. So similarly, by duality, you should have something else that works for high inputs.
Can we make a statement like capacitance increases, but majorly the gate capacitance?
Correct. Yeah. Yeah, that's true. I mean, should be slightly careful. All capacitance will increase by the same amount, but typically the gate capacitance will be much larger than other capacitance. So delta C will be higher with respect to gate, but if you just see delta C by C, it might be similar. So now we also have another transistor, and this is called PMOS. So to turn this switch on, what do you apply at the gate? Or to switch it off, what do you apply at the gate? PDD. That is off. To turn it on, what do you do? Fine. And this is this. Remember that typically we want our clock signal like this, going from 0 to VDD. When this is clock is low, you want this to be off, and this is high when you want this to be on. For a PMOS it is inverted, so you feed a complement of my control signal to the PMOS transistor. So otherwise it's the same thing. So you can again find the on resistance. It is the same thing. It will be mu PC OX W by L into source to gate voltage minus the threshold voltage. Same thing, nothing changes, only the gate to source flips as source to gate, blah blah blah. So here when the switch is on, what is the source voltage? What is the source voltage? V in. Gate? When the switch is on, the gate is 0. So this basically reduces to this. Right? So again, once you have an equation, you always go and plot it to get some visual interpretation. So if I plot it, it's just a hyperbola. Correct? Yeah. Shifted in time or shifted in x-axis. This is basically mod VTH. So here it's apparent, again this works well for within quotes large voltages and not a great switch for small voltages. But otherwise everything we saw for an NMOS transistor with respect to nonlinearity holds good, right? So now you have something that's working for smaller values, something that's working for larger values. What do? You put both of them so that you get the best out of both. So let's say you have normal NMOS switch clocked at 5. This works well if the input is smaller. If I keep increasing the input, this is not conducting. So then you try to take the help of the other fellow. Feed the complement block and then use it. Right? So this is the CMOS switch, or often called the transmission gate. Let's try to see what is the on resistance for this guy. So I have two of them in parallel. So the effective on resistance is parallel combination of these two, right? So again, if I find the on conductance, it is the sum of the two. Okay. So I will directly write the thing. So for NMOS, the conductance was mu1 COX W by L times VGS minus VTH, that was this. For the PMOS, the same thing. Let me quickly write it. It's V in minus mod VTHP, right? So now let us say I choose these two guys to be equal. Okay. If these two factors are equal to some beta, what happens? V in cancels. You just end up with some beta times VDD minus VTH of the NMOS. Right? So here, if I change the input voltage, do you think the on resistance changes? No. My on resistance is not depending on the input. It's a good thing or a bad thing? Good thing, because earlier for an NMOS switch, since my on resistance was dependent on the input voltage, I had nonlinearity, right? So here seems like I've gotten a nice candidate whose on resistance is independent of the input. And again, you can make visual sense of this. So if I sketch the on resistance, for the NMOS we had something like this. For PMOS we had something like this. We put the two in parallel. If I choose mu1 COX equal to mu p COX blah blah blah, then the on resistance seems to be constant with respect to the input. So seems like it's amazing. I have gotten a perfectly linear switch. So do you think this is practically possible, or do you find some issues here? When is my on resistance independent of the input? Or let us say, why is this happening here? I have assumed that these two fellows are equal. So first of all, it is practically not possible to guarantee matching these two parameters, because you will have variations from chip to chip. And more fundamentally, the equation we have for on conductance itself is grossly inaccurate, because we have been using the square law approximation for the IV relation. So there itself we have made an error, and on top of it we are making an assumption which is not doable in practice. So because of all this, it won't be something that is flat like this. You will still have variations like this. Okay. So if you have a CMOS switch, once again it is excellent switch for held signals all the way from 0 to VDD. Right? But if I have a time varying signal, you still end up with non-linearity. So you still have to ensure this to be as small as possible. Cool. So in practice, let us say, depending on the speed and the capacitance you have, with the CMOS switch, let's say you can get a linearity of, let us say, 60 or maximum 70 dB. But it turns out there are many applications where you need much better linearity. One simple example is digital audio. So of course you guys we all listen to songs in the digital format, but remember it's all recorded in some studios, say Rahman studios. So there it's digitized, because someone is singing analog signal, it is sampled and digitized, and the resolution for digital audio is more than 16-17 bits. 16-17 bits corresponds to greater than 100 decibels of SNDR. So there if you go and use a CMOS switch, this might not work. So there is a problem. So of course whenever there is a problem, no need to worry, you should jump right in, because just like if everyone is following healthy lifestyle, doctors will have no job. If there are no problems, we will have no job. So this is a problem and people have already solved it. Let's look at what is the solution.